Hello everyone, in this video we're going to look at forces. Now, anytime you want to solve a problem with forces, essentially you use Newton's second law repeatedly. So Newton's second law says that the net force on an object, which is also equal to the sum of all of the forces on it, are equal to its mass times its acceleration. Now this is a vector equation, which means we can break it down into its components. So if you add all of the x forces together, that'll be equal to the mass times the acceleration in the x direction. And if you sum all of the y forces together, that'll be equal to the mass times the acceleration in the y direction. Okay. Now let's do an example. Let's suppose that we have a mass at the top of a ramp. So suppose this ramp is 10 degrees. And our mass is the top of it like this. The ramp is 5 meters long. And we have a coefficient of kinetic friction of 0.1. Okay. And so we want to know two things. One, what is the acceleration of the object? And two, how long does it take to get to the bottom? Okay. And so we could do this problem different ways. We could do it with energy, but this video is on forces. So we're going to do it with forces. So the first thing you should do in any force problem is draw a free body diagram. So we're interested in this mass. So we're going to represent it as a single point, and we'll draw all of the external forces on. So we don't care about the internal forces because they can't actually cause it to move. So we don't have to worry about the chemical forces holding it together or anything like that. Okay. But it does have some external forces on it. It has gravity, which is going straight down. So we'll label that W for weight. It has the normal force, which is the force of the surface pushing back up on it. And it's going like this. The normal force is always perpendicular to any surface that it's on. And it also has friction. Now this thing wants to slide down our hill. So our force of friction will oppose that. Okay, and we'll assume that it starts moving the instant that we place it here. And so what type of friction is it? It's kinetic friction. Okay. Now our next thing to decide is what coordinate system to use. Now in a problem like this with a ramp, we could use the regular coordinate system if we wanted to. But then only one of our forces is along our axis. So our weight would be along the negative y-axis. So instead, we can simplify this problem by using a rotated coordinate system. So if I just redraw my little mass here, we use a coordinate system where we have one coordinate going along with the ramp. So we can call that x prime. You can call it x or whatever you want to. And we also have another direction which is perpendicular to this. We'll call this one y prime. So once again, you could call it y or whatever you want to. Okay. So now our normal force is already along the positive y prime axis. Our force of friction is along the negative x prime axis. But we still have gravity, right? Our gravity is just going straight down. And so we need to fix that. So it has some part that goes down the slope, and it has some part that's perpendicular to it. So we've drawn a right triangle here. And it's actually similar to this full triangle. So here's the right angle in this triangle, and here it is for this one, which means that this angle is 10 degrees. That's our 10 degrees. Now the magnitude of our weight is mg. That's always the magnitude of our weight. So if we split this into components, we have some part that goes down the slope, and that's our mg sine of our 10 degrees. Because it's the opposite of this angle. And our adjacent side then, which is perpendicular to our ramp here, is mg cosine of 10 degrees. Okay, so now we've broken down all of our forces into our axes. And so now we can sum the forces in the x direction and in the y direction, or in this case, y prime and x prime. So let's do the y prime direction first. So in the y prime direction, we have the normal force, which is going along positive y. So we'll give it a positive sign. And we have this component of gravity, our mg cosine, going along the negative y prime direction. So we'll give it a negative sign. Okay, and this is equal to our mass times our acceleration in that direction. Now, luckily for us, our acceleration in the direction perpendicular to the slope is 0. In fact, anytime you have an object moving along the surface, its acceleration perpendicular to that surface will always be 0. So if our acceleration wasn't 0, that would mean that our block here would have to be having a changing velocity either off of the ramp or into the ramp. So that's not happening. It's going to just stay along this ramp like this. So our acceleration is 0. So if we switch this around, we can see that our normal force is equal to our mg cosine of 10 degrees. Okay, now we're ready to sum the forces in the x prime direction. So in our x prime direction, we have friction, which is going along our negative x prime. So we'll put a minus sign with it. And we also have this part of gravity, which goes down the slope. Down the slope is positive, so we'll give it a positive sign. And this is equal to our mass times our acceleration in this direction. Now this time, this won't necessarily be 0, so we have to keep it here like this. Okay, now what else do we know? We also know the expression of our kinetic friction is our coefficient of friction times our normal force. Now we already found the normal force here, so our force of friction is our coefficient times mg cosine of 10 degrees. Okay, so now we can put all this together and minus the friction force, or minus our coefficient mg cosine of 10, plus our mg sine of 10 is equal to our mass times our acceleration down the slope. Okay, now every single one of these terms has a mass in it, so we can simply cancel it all out, and we'll see that our acceleration is g sine of 10 minus mu sub k g cosine of 10 degrees. Okay, now we know what all these things are. Our mu sub k is 1, our g is 9.81. So we can just plug this into our calculator. And if you do that, then you get 0.737 meters per second squared. Since it's positive, that means it's accelerating down the slope. Okay, but that's only half of our problem. The other thing that we want to know is how long does it take to get to the bottom of the ramp? Okay, and this is something that is often done in force problems. Since you find the acceleration of an object, you can also add in kinematics. Okay, so we can use our kinematic equations then to figure out the time that it takes to get to the bottom. All right, now what do we know? We said that this thing starts from rest. So our initial velocity is 0 meters per second. We just found our acceleration down the slope, which was 0.737 meters per second squared. And we also know what our change in our x is. So if we go back here, our mass started at the top of the ramp, and we want to know how long it takes to get to the bottom. So that distance then is 5 meters. So our change in x is 5 meters. We could call this x prime if we want to, whatever. All right. Now our kinematic equation says that our change in x prime, if you prefer, is equal to our initial velocity times time plus 1/2 our acceleration times time squared. Okay. So we said this thing was 5 meters. Our initial velocity is 0, so this term it doesn't exist. Okay, so we're just left with this equation. We know everything but time, so we can solve for it. And we get plus or minus 3.68 seconds. So anytime you take a square root, you have to remember that there's a positive and a negative root. Now in this case, it obviously doesn't make any sense that the object hit the bottom 3.68 seconds before you let it go. So our answer is 3.68 seconds. Now we could also find the velocity if we wanted to, like this, or find whatever else we want. But now one trick that we can add to these ramp problems is say, okay, well, what happens if there's a horizontal surface below? So after the object slides off the ramp, it continues sliding, okay? So let's suppose that our coefficient of friction is the same. Okay, and the way to connect these two things is that our final velocity on the ramp is now our initial velocity in this problem. So once we slide off the ramp here, our forces have changed, and we have to treat it like a completely separate problem. Oops, sorry, I paused it for a second. So we need to find our final velocity on the ramp, which is our 0 meters per second, plus our acceleration that we found, our 0.737 meters per second squared, times our time that we found. And if you put that together, then you get 2.71. That's our final velocity on the ramp, and it will be our initial velocity on this horizontal part. Okay, now let's redo our free body diagram because it's a completely separate problem here. And we have the normal force going up. We have gravity or our weight going down. Since it's moving this way, we have our force of friction opposing that motion. Okay. Now, in this case, the simplest coordinate system to use is the regular one. So y will be our vertical, x will be our horizontal, and all of our forces are already along one of these axes. So now we can sum our forces in the y direction, and we see that our normal force minus our weight, remember weight is mg, is equal to our mass times our acceleration in the y direction. But just like before, this thing is not coming off the surface or going through it, so our acceleration in that direction is 0. We can also sum our forces in our x direction. We only have one, and it's friction, and it's going along the negative x-axis. So we give it a negative sign. Now, just like before, we know that our force of kinetic friction is equal to our coefficient of kinetic friction times our normal force. If we look at our first equation here, you can see that our normal force is equal to mg. So this is just mu sub k mg. And this thing is equal to our mass times our acceleration in the x direction. So minus mu sub k mg is equal to m times our acceleration in the x direction. We can cancel out the masses, and our acceleration is minus mu sub k g. Okay, now let's suppose we're trying to find the time that it takes for the block to stop. There are other things that you could find, but this would be a common one. So first off, let's figure out the number for our acceleration. It's minus 0.1 times our 9.81 meters per second squared. So it's minus 0.981 meters per second squared. Now, like I said before, our initial velocity now is our final velocity at the top of the ramp. We want to find the time that it takes to stop. So our final velocity is 0. Okay, and so we can find the time using our kinematic equation. Like this, our final velocity is our initial velocity plus at. So final velocity is 0. Our initial velocity is our 2.71. And this has to be added to our acceleration, which is negative, recall, times our time. So if you solve for this, then you'll find that time is 2.76 seconds. So that's how long it takes the block to stop after it slides off the ramp and onto this horizontal part. All right, so that's pretty much all you can do with forces. You have some set of forces, you figure out the acceleration, and then there can be kinematics added on at the